Uh, Good morning. Let us revisit quantum measurements once again. And this is going to be useful for people who've already seen this as well. So far we have been concerned with been concerned mainly with something called as the projective measurement. Uh, so what happens is that let's say you can express your quantum state into an orthogonal set of eigenstates of a Hermitian operator which is being measured. So psi I are the eigenvectors of observable A. Now, upon measurement, you get one of these psi i's with a probability Ci squared, where Ci is this constant. This is the Bond rule. So in general, quantum measurements are much richer than just projective measurements. And the generalized measurement scheme, which we are going to develop now, includes projective measurements as a special case. So in general, measurements are described by a collection of operators they are called as measurement operators. Index M here, the lower index M, refers to measurement outcomes refers to measurement outcomes. Now, if state of the system, let's say the state of the system just before measurement is psi, then the probability of obtaining outcome M is given by this quantity, which is really the inner product with the measurement operator applied to the state, and this is the dual. And what is the final state? The final state is given by, let me call it psi prime. I'm normalizing the final state. So you can also regard this as the postulate of quantum mechanics. So in the parlance of our density matrix formalism, let's say my state was rho before measurement. So what happens? The probability of obtaining outcome M is nothing but trace of this guy. And my final state rho prime would be given by this guy, just normalizing it. Also, I have the completeness relation for these measurement operators. They sum to identity. I mean, you can see this because all my probabilities of outcomes should sum to 1. I should get one of the outcomes. And that boils down to and since this is true for any state, true for any state, this implies the completion relation. So that is the generalized measurement formalism. So of course, how come these things are important? We'll see many applications of the generalized measurement formalism. And let's see. So we can also recover projective measurements, which we've already studied. We can recover from the generalized measurement formalism. Formally, the projective measurements, which you study in undergraduate quantum mechanics, let's say I have a Hermitian observable whose spectral decomposition is given by the eigenvalues and the projectors or the eigenvectors, then the probability of getting outcome M is just the inner product and the state after measurement is just the projector I hit with the state and I normalize this with the probability. And again, for projective measurements, of course, I had the completion relation in general for generalized measurements. And not only that, what do I have? If I have a projective measurement, then these are my measurement, let's say these were my measurement operators. I also have the fact that they are projectors. I'll have this relation. Also, let's say I had a observable, I could have expressed this guy as this. The average value of M is nothing but I get M outcome with a probability of this guy. This is the probability. This is the value of the outcome. This gives me the average value of the Hermitian observable, which is nothing but expectation value of m, which you already know. So this is a useful formalism. Well, over here I've used m's. You can might as well replace it by pm's. It's the same thing. That this is comparison with the generalized measurement formalism. What happens to generalized measurement formalism when you have projective measurements? Okay, so far so good. So just a warm-up exercise. Let's say I have a problem of distinguishing quantum states. This is just a warm-up for what we are going to study now. So let's say I have orthogonal states. Psi 1, psi 2, psi n. These are all orthogonal states. Now I can define projectors, these guys, and the probability of getting the ith outcome is going to be the projectors. I can write the projector. Let's say I'm acting this projector on state j, some state j, and I'll have a size of j. That gives me delta ij. So probability of getting the ith outcome is equals to 1 if I is equals to j, or is equals to 0 if I is not equal to j. So that, what does it mean? It means that the state can be discriminated or distinguished unambiguously. So that's the idea. As long as my states are orthogonal, psi I was orthogonal to psi j, uh, I can use projective measurements or these measurement observables which will turn out to be projectors. So these were my collection of the measurement observables, and I'm going to recover either one when my projector index coincided with the state I was applying it on, or I'll get 0 otherwise. So my state can be distinguished. I'll get a probability I equals to 1 only when I is equals to j, or I have identified the projector with the state. In other words, I can discriminate the state unambiguously. What about non-orthogonal states? See, intuitively, you already know that you cannot distinguish non-orthogonal states. And what's the basic idea? The basic idea is that let's have phi I and phi j as two non-orthogonal states. Geometrically speaking, this is how I represent two non-orthogonal states. They are vectors. I can always express phi I as some component phi j. I'm just breaking them into parts, into a component in line with phi j and a component perpendicular. I'm just resolving phi I in a basis phi j and a vector phi j perpendicular. It's a two-dimensional thing. So therefore, while distinguishing phi I and phi j, I'll always get a component have some probability of mixing I for j because of this thing. So therefore, while distinguishing or trying to distinguish phi I and phi j, one will always have some probability for mixing I for j. That's because I'm going to hit it with the projector, and when I'm going to hit it with the projector, I'm always going to have some support of phi I in the phi j direction and vice versa. So I'm always going to have some ambiguity in it. So that sort of is the basic idea that why I cannot distinguish or discriminate non-orthogonal quantum states. Any projector is not going to work because that projector is going to give some support in the direction of the other state. Okay, so that brings us to another formalism which is called as the POVMs. It's a fancy name, POVM formalism. The acronym stands for positive operator valued measure. So let's look at it. What does this formalism is, and what are the advantages? This is again a formalism to describe quantum measurement. So in general, quantum mechanics provides information about two things. I mean, by quantum mechanics, I mean quantum measurements. Probability of outcome of measurement, also post measurement state of the system. And as we have already seen, these are the set of operators that furnishes this. That is probability is given by these guys, and my state is state after the measurement is Now, suppose we are interested in only one, the point number one, which was probability of outcome of measurements. We have uh, so we don't care about what is going to be the state after the measurement. So in some sense, we are interested in this structure because this structure indeed describes the probability. The rest is my state. So let's define another set of operators as these guys. So mind you, what are the properties? Well, EM are positive operators. You can see by definition, EM is a positive operator, is or are positive operators. I had these guys summing to 1. Identity implies sum over all the EMs is an identity. And of course, the probability of getting an outcome M was this guy. This formalism is known as the POVM, or the positive operator. We'll come to that thing in a minute. Positive operator, it's a fancy name, valued measure. Formalism. And the set of operators EM are called as the POVM elements. And notice that they are sufficient to determine the probabilities of the different measurement outcomes. So to summarize, what does the POVM formalism does? POVM formalism POVM formalism gives a probability to outcomes M for the state psi. So in other words, given the outcome indexed by M and the state row or psi, doesn't matter, the density matrix. This is the density matrix. This is the outcome index. And let me say this is a POVM formalism. This gives me the probability of the outcome, which is nothing but the trace of this guy. Of course, this point to be noted is that these formalism, we started from the collection of, remember we started with these guys, M's of M, which were the collection of our measurement operators. And note, there exists a set of measurement operators defining a measurement described by the POVM collection E of M. So one can go from E of M to at least describe some measurement. So how do we do that? How do we prove that? Well, just choose M of M equals to square root of E of M. We already have, we would know, we can show this guy is going to be an identity, which is going to be sum over all the E's of M. This is the identity. Therefore, this collection describes a measurement with POVM set. It means this measurement is going to have exactly the same measurement statistics as given by the POVM set. So what is the advantage or an example of the POVM formalism? So example of the POVM formalism. Suppose Alice gives Bob either the zero state or the state, which is the eigenstate of the X operator. So we know that Bob cannot distinguish two non-orthogonal states perfectly. We already saw that because you will have some support of one state over the other and then you're going to mix it up. But is there a way to distinguish these states some of the time but never make an error of misidentification. So that means that, okay, Bob says whatever Bob says confidently without any error. Some of the times he's able to distinguish 0 from the plus state, but he never makes an error. So think about it. At some level, this looks like how is he going to do it with projectors? Certainly, it cannot be done with the only projectors, simply because using projective measurements, he cannot distinguish perfectly two non-orthogonal states. But here the challenge is different. The task is not to always distinguish them some of the time, but at the same time never make an error. So consider, think about it. You may pause the video here, think about it. But for the answer, consider the following POVM elements. E1 is this normalization. You can just ignore it for now, in the sense that this is just to, but the essence of the idea is in what goes over here. Similarly, I'll have another POVM element which is going to be and finally E3 is nothing but 1 minus E1 minus E2. So this is my 3-element POVM set, and what's going on? I'll just write it again. Write it again. So what does, just think about it, what does the occurrence of E1 imply? Well, since E1 was something orthogonal to the state 0, this implies that Bob was never given the state 0. Otherwise, E1 would have never occurred. So that implies Bob has the state, this guy. Similarly, occurrence of E2 implies Bob has been given 0. Otherwise, E2 would not have occurred at all. What about the occurrence of E3? Well, the occurrence of E3 implies that maybe Bob has either 0 or the plus state. And this is going to give you the case where Bob is not sure, but he won't make an error. At least some of the times, with probability of occurrence of E1 and E2, Bob can tell you unambiguously whether 0 occurred or 1 occurred. If E3 occurs, Bob will just say, I don't know. So that's the advantage of the POVM formalism. Notice we just dealt with the measurement statistics. We never bothered about actual measurements or the final states. We were just interested in what are my outcomes, what sort of final outcomes I desire, and what are going to be the measurement statistics of those outcomes. So we will be using POVM formalism also in quantum information when we are interested in the measurement statistics, not really the final state. Of course, one can easily show, let's do it on the next page. One can easily show that if my POVM elements are given by these guys are the POVM elements, then my corresponding measurement operators are given by these guys, sum unitary times square root of EM, are the valid measurement operators. Of course, since you can see that this is being satisfied, this sum to the identity, and also the probability of outcome M is given correctly. That's all I need. So what do I conclude? I conclude there is always a unitary freedom in choosing measurement operators corresponding to POVM elements. So what's our conclusion? Our conclusion is that the measurement formalism in quantum mechanics is much richer than just projective measurements, depending upon the suitability of the experiment and what exactly we are interested in. We are going to use either the POVM formalism or the generalized measurement or the projective measurements. So armed with everything what we have studied right now, the density matrix formalism and the generalized measurements, let's cap off this module with the postulates of quantum mechanics in terms of the density matrix formalism. So what's my postulate 1? Postulate 1 is associated with any isolated system is a complex let me write it completely. Any isolated is a complex vector space. That is my postulate 1 within a product. And the system is completely described by described by density operator rho. So what are the properties of rho? Rho is a positive operator. Rho is a positive operator. Trace of rho is 1, and rho is, if I had a ensemble interpretation or probabilistic interpretation, I can write rho as a convex combination of some constituent rows of I. So that just means that rows of I in my ensemble occurs with probability P's of I, then my density matrix would be rho. What about the postulate 2? Postulate 2 is that the evolution of the density matrix is given by a unitary operator, unitary evolution. My postulate 3 has to do with the measurements. So quantum measurements are described by a collection of measurement operators such that the probability of getting the outcome M is we've already seen that, and the state after the measurement, state after the measurement is divided by trace of this guy. And let's just cap it up. What's my postulate number 4? That just says that if I have a composite system, the state space of a composite system is a tensor product. So I have n systems, the state space would be given by a tensor product where system 1 is prepared in row 1, 2 is prepared in row 2, so on and so forth. So that is essentially the postulates of quantum mechanics in terms of density matrices and generalized measurements. And this is more general than how we introduced initially quantum mechanics, but this is going to be more useful since we are going to deal with density matrices and open quantum systems going forward. Thank you.